All right, 3.11 is the last section in Chapter 3, and we're going to talk about what's called the hyperbolic functions. Combinations of e to the x and e to the negative x occur very frequently in calculus and in other places too, that we give them special names. In many ways, they are similar to the trig functions. You'll see that in what we're doing here, just the notation and identities and things like that. And they have the same relationship to the hyperbola that the trig functions have to the circle. For this reason, we call the set of functions here the hyperbolic functions. Okay? Individually, we call this hyperbolic sine, hyperbolic cosine, hyperbolic tangent, etc. Okay? The way that we define hyperbolic sine x is e to the x minus e to the negative x all over 2. The way that we define hyperbolic cosine x is e to the x plus e to the negative x all over 2. The way that we define hyperbolic tangent x is hyperbolic sine x over hyperbolic cosine x. The way that we define hyperbolic cosecant x is 1 over hyperbolic sine x. Hyperbolic secant x is 1 over hyperbolic cosine x, and hyperbolic cotangent x is hyperbolic cosine x over hyperbolic sine x. Okay, so now already you can probably see some hidden trig stuff, but careful, we're not doing any trig. Okay, don't get this mixed up with trig. There is 0 trig in this section, okay, or at least at the moment. I'm working with exponentials, right? I'm working with formulas involving e to the x and e to the negative x. H is not a constant, so I wouldn't think of this as sine of h of x or cosine of h of x. If you're doing that, you're still, thinking about trig stuff, and we're not nothing about this is trig. Okay. Now, there is a relationship with the hyperbola. I mentioned that, just like the trig functions have a relationship to the circle. Okay, hence the name hyperbolic functions. On this other handout, which is in your notes, I've got, here's the graphs of all 6 of the hyperbolic functions along with their domain and range. Okay, I've got the name of the function up top, the graph, the domain and the range. Okay, now these are not functions that are, these are not graphs that you'll need to have memorized. Okay, the hyperbolic functions will come up here and there for different things, but they don't really beat you up with it. Okay, especially not with the graphing. Now, make sure that you know how we define like hyperbolic sine x and hyperbolic cosine x and hyperbolic tangent x. The other 3 are the reciprocals, right? So just like with the trig functions, we're doing stuff with reciprocals and quotient identities here, and because those will come up here and there, right? There's identities for the hyperbolic functions, just like there's identities for the trig functions. On that handout, I've got some hyperbolic identities here listed, some ones that are ones that we would use in this section, I guess. So one of them is hyperbolic cosine squared x minus hyperbolic sine squared x is 1. Okay, let's see where that is coming from. Well, hyperbolic cosine x is defined as e to the x plus e to the negative x all over 2. I'm squaring that. Minus hyperbolic sine x is defined as e to the x minus e to the negative x all over 2. And I'm squaring that. Okay, now I want to simplify this and show that I get 1. Well, 2 squared is 4, right? So you're going to have a 4 in the denominator of both of these. Let me just go ahead and get a single fraction on this. And in the numerator, I'm going to have an e to the x plus e to the negative x squared, which I've written those 2 down, minus e to the x minus e to the negative x squared, which I've written those 2 down. Okay, and then I'd want to FOIL these out and then FOIL these out. also distribute the negative into the terms there at the end. So I've done that. E to the x times e to the x would be e to the 2x, or e to the x squared is the same as e to the 2x. The outer and the inner terms, okay, so we're looking at e to the negative x times e to the x. Keep the base and add the powers. That'd be e to the 0. Anything to the 0 power is 1. So I'm going to have 1 plus 1 is 2 in the middle. The last term, positive times positive is positive. E to the negative x times e to the negative x, that'd be e to the negative 2x. Minus, then you'd FOIL this part out. Okay, e to the x times e to the x is e to the 2x. The outer and inner terms, so we're looking at negative e to the negative x times e to the x, that'd be negative e to the 0. Anything to the 0 power is 1, right? So negative 1 minus 1 is negative 2. But then you're going to bring in this negative, so we get a plus 2 there. And then at the end, negative times negative is positive. E to the negative x times e to the negative x is e to the negative 2x, but you're going to bring in this negative into the last term, so it's a minus e to the negative 2x. Okay, and now we're going to have some things cancel here. E to the 2x minus e to the 2x, those are gone. E to the negative 2x minus e to the negative 2x, those are gone. And that leaves us with 2 plus 2 is 4, divided by 4 is 1. Okay. Now, if we use that identity that we just proved there, and we divide both sides by hyperbolic cosine squared x. I've done that here. Hyperbolic sine x over hyperbolic cosine x is how we define hyperbolic tangent x. I'm going to have a hyperbolic tangent squared x, since I'm squaring both these things. 1 over hyperbolic cosine x would be, by definition, how we define hyperbolic secant x. Okay, so I'm going to have a hyperbolic secant squared x there on the right. Well, let's see here. So that is where this identity is coming from. Okay, just taking this one and dividing both sides by hyperbolic cosine squared x. Of course, I could divide both sides by hyperbolic sine squared x and produce another identity there. Let's take a look at the derivatives of the hyperbolic functions next. So, how about the derivative of hyperbolic sine x? Well, hyperbolic sine x is e to the x minus e to the negative x all over 2. Okay, I'd say let's go right to that definition there, that form in terms of e to the x and e to the negative x. Well, 1/2 is a constant. I can leave that alone. The derivative of e to the x is itself e to the x. The derivative of e to the negative x is e to the negative x times negative 1. Now you're subtracting a negative, so that would mean that you're adding e to the negative x. But e to the x plus e to the negative x all over 2, that's how we define hyperbolic cosine x. So the derivative of hyperbolic sine x is hyperbolic cosine x. The derivative of sine x is cosine x, right? Again, I'm not doing anything with trig here, but there's some, kind of hidden similarities. How about the derivative of hyperbolic cosine x? Well, hyperbolic cosine x is defined to be e to the x plus e to the negative x all over 2. So that's what I'm differentiating. 1/2 is a constant. I can leave that alone. Derivative of e to the x is itself e to the x. Derivative of e to the negative x would be negative e to the negative x. E to the x minus e to the negative x all over 2. That's how we define hyperbolic sine x. So the derivative of hyperbolic cosine x is hyperbolic sine x. The derivative of cosine x is negative sine x. Okay, so careful about that, sign difference there. Let's see, how about the derivative of hyperbolic tangent x? Well, hyperbolic tangent x is hyperbolic sine x over hyperbolic cosine x, and I can use the quotient rule then when I differentiate. So let me do that. The bottom is hyperbolic cosine x times the derivative of the top, that'd be hyperbolic cosine x, minus the top is hyperbolic sine x times the derivative of the bottom, that'd be hyperbolic sine x. all over the denominator squared. So it'll be hyperbolic cosine squared x. And, okay, simplify hyperbolic cosine squared x minus hyperbolic sine squared x. That is 1. So I'm getting 1 divided by hyperbolic cosine squared x. That would be hyperbolic secant squared x. Okay, the derivative of tangent x is secant squared x, so there's a kind of a similarity going on there, right? Now, if you were to differentiate the others, okay, the remaining 3, you'd need to use the quotient rule. I'll just, tell you what they are, though. Okay, so the derivative of hyperbolic cosecant x is negative hyperbolic cosecant x, hyperbolic cotangent x. The derivative of hyperbolic secant x is negative hyperbolic secant x, hyperbolic tangent x. The derivative of hyperbolic cotangent x is negative hyperbolic cosecant squared x. And just to point out the similarities going on with the trig stuff, here's the derivative of cosecant x is negative cosecant x cotangent x. The derivative of secant x is secant x tangent x. There's a sign difference there, right? Derivative of cotangent x is negative cosecant squared x. Okay, and again, I want to reemphasize there is 0 trig on this entire page. I'm not doing any trig. Okay, so don't get mixed up with that. Okay, now there's similarities. I agree, but there's 0 trig on this. Let's take a look at some examples now. So suppose that we have y equal hyperbolic cosine of 1 minus x squared, and I want to take the derivative. Well, that's going to be a chain rule. Okay, so 1 minus x squared is inside of the hyperbolic cosine function. Derivative of hyperbolic cosine x is hyperbolic sine x. Now, I don't have hyperbolic cosine x, right? But I'm going to begin that way. It's going to be hyperbolic sine of 1 minus x squared times the derivative of 1 minus x squared is negative 2x. And I've pulled that to the front. Negative 2x times hyperbolic sine of 1 minus x squared, that'd be my answer for y prime. How about y equals the ln of hyperbolic sine x? Well, the derivative of the ln of an expression is 1 over that expression times the derivative of that expression. So dy dx, or y prime, is 1 over hyperbolic sine x times the derivative of hyperbolic sine x. That's hyperbolic cosine x. Hyperbolic cosine x divided by hyperbolic sine x is hyperbolic cotangent x, and that'd be my answer. Okay, here's another example. F of t equals hyperbolic secant squared of 3t minus 1. This is going to be a chain rule within a chain rule. So I'm going to begin by, I know I'm squaring something here, right? So start with the power rule. Bring the power 2 down, reduce the power by 1. You're going to have 2 times hyperbolic secant of 3t minus 1, and then I got to differentiate hyperbolic secant of 3t minus 1. Well, the derivative of hyperbolic secant x is right here. It's negative hyperbolic secant x, hyperbolic tangent x. Okay, I don't have hyperbolic secant x, right? But I'm going to use that formula, and where I see x, I'm going to write a 3t minus 1. And then I got to finish the chain rule. I got to multiply by the derivative of 3t minus 1. That's 3. Okay, and I've stuck the 3 right here after the negative sign. Simplify this. 2 times negative 3 is negative 6. Hyperbolic secant of 3t minus 1 times hyperbolic secant of 3t minus 1. That'd be hyperbolic secant squared of 3t minus 1. And then we've got hyperbolic tangent of 3t minus 1 that we're multiplying there. Okay, and here's my answer then in simplified form.